do. All right, let's see what we got. It looks like a hard one today. Minimum cost path with teleportations. Let's see if I can handle it. You're given a n by n 2D integer array grid with an integer k. You start at the top left cell, and your goal is to reach the bottom right cell. n minus 1, n minus 1. There are two moves available. Normal move. You can move right or down from your current cell I, j. i.e., you can move. Okay, you can move one row, one column to the right, j to j plus 1, or one row down, I to I plus 1. Sure. Cost is the value of the destination cell. Cost is the value of the destination cell. Alright, you can teleport from any cell to xy here, such that the grid at xy is less than the grid at ij. The cost of the move is 0. You may teleport the most k times. Okay, so you move a j, so the cost is always to the destination cell's value. The cost is always moved to the destination cell's value. No, the cost of this move is 0. Okay, the cost is either the destination cell value if you do a normal move, or 0 if you do a teleportation move. The teleportation move, you can only move it if you go from a smaller value to a bigger value place in the grid. Okay. Return the minimum total cost to reach cell n minus 1, n minus 1 from 0, 0. What's the values here? The grid. The grid has value from 0 to 10 to the 4th. Interesting. So if your current spot is like cost 100, you can teleport to something that costs 4,000. It costs you 0. Otherwise, you'd have to pay to get into pay 4,000 to get to this grid. Okay. Try to figure out what the strategy would be here. Is the if you had just normal moves from 0, 0 to the ending cell, just had normal moves from there to there, you would try to find the minimum path, the path that crosses through cells that have the lowest value. And if you were to not alter that path, but somehow use teleportations within that path, then you would maybe get to some high value cell and teleport to the second highest value cell that's later on in the path. Like maybe the highest value cell in the path is 5,000, and there's like another 4,500 later on in the path. So you teleport from 5,000 to 4,500. No, that doesn't work. No, you'd almost. No, you'd probably just like teleport from your starting point to your highest point. Would that work? Oh man, this is this is weird. Teleport from a low to a high, and then use normal moves to go down. Normal moves to go down to a low point to jump to another high point. So let's say like your high values are like 5,000, 6,000, and 5,000, 6,000. No, it has to be. can't be just 5,000, 6,000 because then you just jump to 6,000. So I think what would happen is you would jump to, let's say k is 3, you jump to like the 3 highest points in your path, where those 3 highest points have to be in descending order. Like you jump to 8,000 and then to 7,000 and then to 6,000. Like you jump from your start to 8,000 and then you go down normal paths down to something below 7,000 and you jump to 7,000. And then you go something below 6,000 and jump to 6,000. Except if the 8,000 was followed immediately by 7,000, then you'd have to have, there has to be a gap of at least one thing. Interesting. Oh man. Just trying to visualize what the strategy would be here. 1, 3, 3, 2, 5, 4, 4, 3, 5. What the hell is that? The grid. You're given a grid, n by n grid, integer k. You start at the top right or top left, move to the bottom right. Oh, I was confused with yesterday's question. So 1, 3, so 1, 3, 3, 2, 5, 4, 4, 3, 5. So it's a pathway. You just jump from 1 to 5, no? You can teleport from ij to xy's such that grid of xy is less than grid of ij. Oh, I was thinking this backwards. I was thinking grid at ij is less than grid at xy. No wonder I was so confused. Yeah, you have to jump downwards rather than have to jump upwards. So you have to go, so 1, you can't jump anywhere. So I assume you'd go to 2 maybe. And then 2, you can go probably 4. No, 2 go to 5, and then jump from 5 to 5. Go 0, 0, move to 2, move right, move to the 5, 7 cost, jump to the end. Okay, yeah. Huh. 1, 2, 2, 3, 3, 4. So here you can't ever jump to the end. So this boils down to just a simple, what's this lowest cost path? And both 1, 2, 3, 4 or 1, 2, 3, 4 is going to give you 10. No, it's going to give you 2, 3, 4, 7, 9. I can do math, sure. So I think this is a heap again, similar to yesterday. Heap traversal of possible places. Yesterday had an array of costs where the array had the places and the cost, the minimum cost to get to that place. probably can do something similar here. The one thing about moving moving to the right and moving to the bottom is it's always kind of forward movement. It's never backwards movement, so you can tell when something is kind of in the future, moving towards the end goal versus not. So like this 3 can jump to this 3 or this 3, and these 3 are closer towards the end goal. What is the value of k here? K is up to 10. Seems like dynamic programming, I'd say. Storing states where each state is the position and the number of moves. Yeah, this seems like dynamic programming. Dynamic programming. I can spell. I can do it. I can spell. So for dynamic programming, just consider states. Like where your inputs to state, what's your output? So the inputs to a state would be position in grid, which is going to be a row column, and the number of moves spent, which is something less than or equal to k, right? And the output is going to be just the minimum cost to reach that state. Consider stats. Consider states. And then you have just some sort of transition between states. So your transition between states is going to be a movement or teleportation. A normal movement or teleportation. And then just trying to find how to get to the last state. Last state, kind of. State with row equals n-1 column, n-1 and k, and spent is less than or equal to k, right? Transition is going to be somewhat an issue because you can jump from a position to kind of a later position, spending a teleportation it's like but you can then jump to every so if you go to 3, you can jump to any later 3 or 2 or 1. Jump to any later 3, 2 or 1. If you go to 2, you can jump to any later 2. I guess if you're on a certain diagonal, that means you're kind of at the same relative position. So you're on this 2 or this 2, which is on kind of the main on the same minor diagonal. Minor diagonal being from top right to bottom left, because it's the same number of rightwards or bottom movements. Jumping from 3, so how would you handle the jumps? It doesn't make sense to try to jump to every possible later position that has a lesser cost. That means that for every position you have to consider pretty much all the other positions to jump to. Seems like a lot. Grid has, I mean, it's an 80 by 80 grid, so maybe it's not that much. 80 by 80. So if it's like every position, jump to every other position, that's like 80 to the 4th, maybe. 80 to the 4th times 10 for K. I think that might be too much. Yeah. That's 409 million. 409 million. For every position, go to every other position. Maybe it's just 80 to the 4th, and you're not worrying too much about states. Even if it's, well, the factor of 10 doesn't matter. If it's just 80 to the 4th, that's 409,000, which is doable. No, it's 40 million. It's still a lot, I guess. So if you have a certain position, is there a way to know what is the best place to jump to? So 2 goes to another 2. There are no low 2s. 3 goes to another 3. So it has 2 goes to another 2. 3 goes to another 3, 2, or 1. Interesting. If I'm at this 2, I can only really jump to, even if there was like a 1 right here. If I'm at this 2, actually, now that I think about it, anytime you're at a particular position, you has to be at least, each movement has to be increasing, I want to say. Otherwise, why wouldn't you teleport to that spot? Guess it has to be, each movement has to be moving to an increasing or equal, I guess. Could be equal because unless you run around of teleportation, teleportations could be 0. Okay, if teleportation is 0, that's kind of like just finding the least path. If teleportation is 1, no, it's not true. Could teleport to try to get rid of some stuff in the path, then have to just find the minimum path after that. I guess it's possible. I guess it's possible that you teleport to kind of another position that's kind of impossible otherwise. Like, let's say you go to, let's say it was like 1, 3, 2. Let's say these were 40, 50. Yeah, let's say it was something like this, right? So the optimal pathing would be, in this case, 1. Go 1 to 2 here, and then teleport from 2 to this 2 here, and go to 4, 5. Even though these 2 are not even, there's no path from this 2 to this 2 that you could even do. Moving rightwards and downwards. Oh. Interesting. Now to, so we should just start by considering no teleportations. Find the min path from each cell to the end. That might not actually be that simple. Find the min path from that cell to the end. Hmm. by 80, so there's maybe 6,400, is that right? 6,400 value. Is it possible that I associate each value to the cost to reach the end from that value? Anywhere in this, anywhere in the thing, cost to reach the end from that value? Is that reasonable? Like, just build some sort of cost table, cost array, and then sort. Sort, remove the duplicates. Sort, remove the duplicates. From go 1 to 2 to 3. One to 2 to 3. The teleportations makes the transition between states quite complex. You can transition to states that are not just adjacent. but to any later state. Roughly. So it's possible you jump backwards, right? Let's say you have let's say you have 1, 2, 3, 4, 5. Let's say there's a blocking 1,000, 1,000. And then there's like just 5, 6. I can type 7, 8, and 9. So even though this 5 is actually closer to this end state, end position, you want to do a very long path to get to this 5, and then jump to this thing, and then do this long path to get to the end, rather than try to spend one movement to enter into this high cost position. And you can obviously extend this out extend this example out, or come up with another example where like literally you take an extremely long path, jump all the way to something near the start, and then take another extremely long path to the end, just to avoid crossing some high cost zone. Okay. It's good to know that you're not always going to want to jump to something that's closer towards the end position. You might want to jump backwards or to a position that's farther away. Phase 1, then you should never. Phase 1, then if you ever enter in a position whose value is greater than or equal to the end position, then that should basically terminate. You should basically jump to the end, right? That's if k is 1 or more. K is 1 or more, all positions that are greater than or equal to the end position is treated as the end position, I think. If k is 1 or more. So when you're at a particular position and you want to teleport, you should teleport to the falling position, teleport to any other position that has the least cost to the end from every position Interesting. Transition, transition, transition. So if I do backwards, I wonder if backwards or forwards is. Maybe it's just brute force. I just need to, from every position. Consider every other position. That doesn't seem right. Every position, consider every other position. Maybe that is right. Oh. From every position, consider every other position. Oh boy. Oh boy, oh boy, oh boy. I think I need to create a sorted list of all positions. Here will be the cost of that position, the position itself. I think I need to know that information. Okay. For every, I guess it's going to be, I'm going to iterate through the grid and convert into these tuples. Grid, I guess it would be M, I'll use rows and columns since I don't like to use M and N. Just less easy for me to interpret. Rows is the length of the number of grid arrays. Arrays and grid. Calls is the length of the first row. And let's say for R in range of rows, or C in range of columns. For R and C are the row and column indices. I'll say spots appends the tuple that is the value at this position and the indices. Let's sort it. And just double check that this is where I want it to be. So sorted, the lowest cost is 1, position 0, 0, 2 position, row 1, column 0, 3 position, row 0, column 1, 3 position, row 0, column 2, 3 position, row 2, column 1, 4 position, row 1, column 2. Okay, that looks fine. I think I want to have this so that I have a quick way of kind of knowing where it can jump to. Is if I'm at a particular value, let's say the value is 3, I can jump to any position that is less than or equal to 3, which is everything in this order array up to 3, right? For the cost. Alright, if I need my DP matrix, primary matrix. So it's gonna be 3D because there's 3 inputs here. We could also do like a default dictionary where the key is the inputs and then the output is just the value. But the matrix is probably more memory efficient, faster. So the DP matrix is going to be the innermost so I guess it's infinity times k plus 1 maybe? And then that's multiplied by the number of rows for every or blanking range of columns or blanking range of rows. Generally columns plus 1, rows plus 1. That's how you do DP matrices most of the time. Don't know if this should be infinity. The default cost is probably infinity. It has to be high and then try and minimize it. Okay. I think that's one because you want to index using k itself and the movements, and it can be 0 up to k. Alright, if I try to print out this DP, it's just not going to look very well. It's too hard for me to actually figure out whether it's correct sizing. I think it's probably right. K is 2. So it's 3 infinities for every position in a 4x4. Four by four. So now it's just trying to transition between states and figure out how to process the states. I think it's probably heap. Probably heap where you're considering the lowest cost to get to a particular state. If the state somehow reaches the last row or column, then you might be done. Maybe. I think so, right? We're considering teleportations each time. Yeah. So I think this should be probably a heap. If it's a heap, then do I even need a tiny matrix? Because I'm just going to jump to the end. If I reach the end, then I'm done. So if the heap is the cost and the position, the heap is the cost, position, and then number of k movements. Cost, position, k used. Cost, k spent, and then position. Interesting. Cost, k spent, then position. I'll move with teleportations. I'll just call them jumps. Okay. So I'm not sure exactly how to do this. Like I think maybe I don't need a DP matrix if I'm using a heap, to be honest. Okay. Otherwise the heap might be too big. Heap might be too big. Okay. So when I process the heap, I should take the top down of the stack, so the cost jumps row and column is equal to heap dot heap push heap pop. I guess the heap should actually start with the initial position. So the initial position has a cost that is 0. Number of jumps used is 0, 0, 0 is the position. Let's say the current value is going to be grid at this position. So that determines what other things we can jump to. Must be lower than or to the current. I could jump to, I guess I would jump to a neighbor, because the move cost is 0 in that case. Okay, well, let's go ahead and consider jumps. And then, well, maybe I should consider the movements. So I guess here I can consider a downwards movement. let's consider rightwards movement. So if column is not equal to cols minus 1, col doesn't equal cols minus 1, so I can move right. And I guess I do use DP here. And the cost plus the grid at the next position, cost plus grid at the next position is less than or equal to dp at this next position where I have this number of jumps. So the cost is less than the cost of the best I've seen to get to that position. Then I'll say here TP, I'll update for that state this new cost. And then I'll need to add it to the heap. So the tuple would be cost plus grid row column plus 1, jumps row column plus 1. Somehow I want to consider jumps that are bigger than that too, or smaller than it. Because I kind of want to, if I can get there, if I can get to a certain position with, let's say, 1 jump at a lower total cost than getting to that same position with 2 jumps, then the 2 jumps should also update maybe. So I should actually do this for every jump. Right. I'm not sure about that, or I'm not sure if that's the best way to handle that. So normal movement going downwards, rows not equal to rows minus 1, and cost plus grid at row plus 1, column is less than or equal to dp of row plus 1, column, this number of jumps, and dp at row plus 1, column, this number of jumps is equal to cost plus grid at row plus 1, column, a push, cost plus grid at row plus 1, column, jumps row plus 1, column. IBM. In theory, it could just be, if it's smaller than or equal to, then I should just update every single thing that's for higher jump as well. So it should be a for loop for this number of jumps or more. Because if you spend more jumps, then you should be getting to that spot with a smaller cost. Okay, consider jumps. So for every cell that has the current grid value or less based on the sorted array. So I think it should be something like for grid value for every entry into this spots array for, I guess I can say that's the G cost, the grid cost. And the, maybe I'll say S cost, spot costs, spot row, spot column, in spots. If this S cost is greater than the current cost here, then I need a break. And I probably shouldn't do this if I have no more jumps. If the current jumps is equal to the maximum jumps, then I think I just continue. So for every spot that has a lower cost than the current, no, this is the current cost here is talking about total cost to get to this position. Current is getting current grid cost. Should somehow use better naming here. What is this thing? Grid, start top right. Cost is the value. I guess this should be value. So the value here, this total cost, that's fine. I think I'll call this current value. Which will determine the max value of the jumping spot. So I guess this is the spot value. Is greater than the current value. And then ignore it. Then stop this loop. Otherwise, consider the jump to that position. So it has to have a lower cost total. So cost is, I guess it's the jump cost is 0, right? So the cost is less than, strictly less than, I think. cost is less than dp at that jumping spot with one more jump. Then dp s row s column one more jump is equal to this cost. And again, maybe this should be a for loop for all jumps plus 1 up to k. Because if you can get there with 2 jumps with some cost, then getting there with 3 jumps and no, it's not true. It should be that number of jumps. What is the logic? So is it somehow possible? So if you improve, let's say I'm doing 2 jumps to get to a certain position. 2 jumps to get a certain position with some cost. How does that relate to getting there with 3 jumps? Getting there with 3 jumps needs to be smaller. So it's not going to be well, I'm using a heap, so cost is always increasing. I'm always evaluating the lowest cost move. So is that right? Always evaluating the lowest cost move. Seen so far. So if I've gotten there with a higher number of costs, higher number of moves, I don't know if I need to update. Is it possible? Get to have changed the matrix to have gotten there with a higher number of moves at a higher cost? I don't can't think of how that could have occurred. Pretty sure this can definitely occur, like just the default infinities. I guess default is infinity, so default is infinity, so it initially is higher. Later on it's okay, I think it's fine maybe. And then I need a heap push. Cost jumps plus 1. The new position I wonder. Does somehow consider all previous positions, which kind of sucks. Does somehow consider all previous positions. Every single one of them. So, for instance, I got to some position with 1 jump, and later on I got to that position with 5 jumps. Should somehow ignore that. I got to a certain position with 1 jump at some low cost, then gain there with 5 jumps. Yeah, actually, yeah, I think I might need to, probably should update for all jumps from jump +1 to k. So if I start with, let's say, a starting cell with 10, I jump to a later cell that has a value of 0 in 1 jump. In theory, I could move from 10 to a neighboring cell and then jump to 0 in 1 jump again, but then it just has a higher cost. But I probably, or jump from like 10 to 5 to 0 somehow. I guess the cost there is just still 0. I think this does need to go through all the other jumps. From jump 1 to jump k. But in theory, jump yeah, the values for each successive jump should be smaller than the previous. Okay. So for every j in range of jumps +1 to k, k plus 1, k plus 1, I need to do this. One jump, 2 jump, 3 jump, 4 jump, 5 jump. Okay, and I think I need to do the same thing for these. For every j in range of jumps to k plus 1, do that. For every j in range of jumps to k plus 1, do this. Lower the EP. I did the update, pushed. Since this is using heap, I think I should be able to stop when I see the last row column. Yeah, because it's not actually traversing it. So I don't have to wait until it reaches this thing at a lower value, because it's not possible to have reached it with a lower value. I'm exploring every kind of low cost possibility. So I think if the row is equal to rows minus 1 and column equals columns minus 1, I can just return costs. It should never go kind of impossible number of jumps. And I think this should never need to return -1, even though I'm just going to add the default return. Maybe I should put it below here. Okay. See how this goes. Does it work at all, or does it immediately crash? Immediately crashes. Out of range. If calls is less than or equal to calls -1, is not equal to calls -1. Cost plus grid at row call +1. I see. What am I thinking about here? I think it's actually, it should be less than calls. I can't actually, so I think it should be less than calls -1. Yes, if calls not equal to, so it can't be the last column. Can't be the last column index. So if there's 3 columns, indices 0, 1, 1 not equal to, guess it should be call not equal to calls -2, but then it can't also be the last column. No, what am I thinking? If it's 1, then it should be fine. If it's 1, it should be index 2. Call +1 is 2. 3 indices, 3 column indices. How is that going out of bounds? Really? Maybe it's the jumps. I guess I'll just print out what I'm dealing with. I'm dealing with the most simple one, all zeros. Cost plus grid at row column +1. How's that going out of bound? What? DP at row column +1 jumps. Unless I somehow made my DP matrix wrong. I guess I must have made my DP matrix wrong. Oh, I think I need bracket here. Oopsie. One. Yeah, oops. Okay. DP of S row S column J +1. Oh, it's supposed to be J, right? Determines the max jumps. Yeah, it should be J. Oh boy. Do 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 do. Might be too slow. Judging by its speed here, I think it's too slow. Oh boy. Yeah. Pay is 3. Hmm. What's the size of this thing? It's a 71 by 77, so not even 80 by 80 yet. Okay, it could be up to 10, so it's not good enough. Maybe the heap is just gotten too large, maybe. So okay, I wonder when I take something off the heap, it might be outdated information, I want to say. So maybe I need to remove outdated information. So if the cost is greater than dp to this row, to this column, with this many jumps, remove it. Okay, well, this is a big number, but did finish it. Yeah, still too slow. Yeah, it's not like I did it wrong. It just didn't finish in whatever time frame it is to do all the test cases, I think. But that's the same as the previous understanding of what went wrong. Cost is greater than how long it takes to get to this thing. Consider the normal moves. Handling the jumps. There has to be a better way of handling these jumps. Somehow I should be able to ignore values in the previous plots, or maybe even remove them from the array. remove them from the queue, store in a queue. At some point, every time I compare to a previous position, it cost me 0. It cost me 0 to jump. From a particular position, assuming I have a jump to use, from the starting position, assuming I have a jump to use, I can use that jump to get to any later position with less or equal to value. I wonder. There's some logic here for eliminating spots from consideration, I think. Eliminating spots from consideration. Interesting. So my heap is always going up in cost. My heap is always going up in cost. And in theory, my heap might be spending all its jumps before it kind of moves up in cost. Spending all its jumps. Is that right? I wonder actually, should it be considering cost jumps, row column? Might want to sort by biggest row and biggest column rather than smallest row, smallest column. Because if you have same cost, you want to look at the ones that are closer to the exit first rather than the ones that are closer to the front. Guess that makes sense. So maybe it should be negative row, negative column. Not sure. I don't know if that's gonna be that much of a difference. So if I add to the heap, it should be the negative version. Uh, Okay, I guess the syntax doesn't work. Oh, whoops. I'll just, whoops. Negative of n row and column. Maybe the syntax did work. Negative. Same runtime. Okay. Never mind. So what was I thinking? I was thinking maybe if I'm going to consider places, I'm going to consider has the heap gone too big to sort? Has the heap gone too big to sort? What is the size of the heap here? $924. I mean, that is kind of slow, so I'm basically inserting into a 924 size heap, which is going to take log of that size to insert into a heap. So like 10 executions. It's not terrible. I don't think that's the issue. Well, yeah, I don't think inserting it into the heap is the issue. If that's the case, I think it's probably just this thing right here. Iterating through all the possible smaller values from a particular value. That's probably making it n squared, or n to the fourth. Maybe. So from particular positions, so you start at 10, you're looking at everything that's smaller than 10 and jumping there. So from 10, jump to the 0, the 1, the 2, the 3, the 4, the 5, the 6, the 7, the 8, the 9. Cost there is 0. And then when you consider jumping to the 9, you consider jumping to the 0 through 8. But why would you consider jumping to the 0 through 8 when you could have jumped from the 10 to the 0 already? Why would consider jumping from if you're jumping from 10 if you're jumping Hmm. If you're spending zero cost, to jump from a 10, I guess my issue is like I'm trying to maximize two things. Jumping, starting position. So if you jump from 10 to 0 through 9, then how to prevent checking or jump from like 1 to 9 to 0 later on, because you should have already tried jumping from that. Hmm. So if you jump from 10, you jump from 10 to 0. Hell, why would you ever consider hmm. Maybe I need to keep track of the highest value in the current path seen so far. The highest value of the path up to this position. Then that would require that keep track of another variable. Highest value. Because if you're at a lower value, if you're lower than the highest value and there are any jumps, then you would already have done it.